Hello everyone, welcome to the channel Top Gate. In this video, I will discuss one disadvantage, one problem that is associated with the FCFS scheduling algorithm that is called as the convoy effect. Fine. So those who haven't seen my previous video about the FCFS scheduling algorithm, you may go to that video first. I'll put the link in the description box of the FCFS scheduling algorithm. So you may go to that video first, watch that video and then come here again, because this video is directly linked to the FCFS scheduling algorithm. Okay. So first of all, I'll try to explain to you with the help of a real world example that what is the convoy effect, and then I'll come here and with the help of these two cases, I'll tell you that how this convoy effect is linked to the FCFS scheduling algorithm and what harm it can do to the algorithm. Clear? So suppose there is a military convoy, and this military convoy suppose has 50 trucks. Fine. And this military convoy is passing through a junction, and to pass through a junction, this military convoy will require at least 30 minutes. Fine. Now suppose you as a person, you also want to cross that junction, and at that very moment, at that very same time only. Fine. But before you could start crossing the junction, the military convoy came and it started crossing the junction. Now you being a single person, you'll only require maybe say 1 minute to cross the junction, and the military convoy having 50 trucks, they will require at least 30 minutes to cross the junction. Now you require only 1 minute, they require 30 minutes, but then also now since they have taken the junction first, since they have started crossing the junction first, so now you have to wait for at least 30 minutes so that that convoy passes through the junction, and then you can only move and cross the junction. However, you only require 1 minute. Clear? So this is the convoy effect, that is the person who requires only 1 minute to cross the junction is waiting for the convoy to pass through the junction for 30 minutes. Fine. So now let's come to this one. I'll discuss this with the help of two cases. What is the convoy effect and how is it linked to the FCFS scheduling algorithm and what harm it can do to the algorithm. Clear? So the first point says that the convoy effect is linked to the FCFS algorithm. So if any time you come across a question that asks you with which algorithm the convoy effect is linked to, your answer will be the convoy effect is linked to the FCFS scheduling algorithm. Clear? And no other algorithm suffers from this problem. Clear? So it is clearly a disadvantage, a problem that is associated with the FCFS scheduling algorithm. Clear? Second point says a process with high burst time makes a process with lower burst time to wait until its completion. What does that mean? That is, suppose we have two processes in a system, and one process is having a very high burst time and one process is having a very low burst time, very short burst time. But the process with the lower burst time is actually waiting for a longer time for the process having a high burst time. So that is a problem in this one. So I'll discuss this with the help of these two cases. We have two cases. Case one, in this one I have two processes P1 and P2. The arrival times of the process P1 and P2 is given as 0 and 1, and the burst times are 50 and 1. So you can notice in this one that P1 is having a very high burst time of 50 time units and P2 is having a very low burst time of only 1 time unit. Clear? So if we make the Gantt chart for this one, so let's make the Gantt chart first. So what happens? We are currently at time 0, and at time 0 I'll see, is there any process which comes into the RAM at point 0? Yes, there is only one process P1 which is coming into the RAM, into the ready queue at time 0. So right now I don't have any option. I'll start with the P1, that is P1 has arrived into the RAM at 0, so therefore I am scheduling it on the CPU at time 0, and since it is a non-preemptive scheduling algorithm, so that we have already discussed that FCFS is a non-preemptive scheduling algorithm, therefore once a process starts, it will not leave the CPU unless and until its whole work is completed. So P1 will start at 0 and it will complete its work at 50 time units. Fine. Now this process completed its work and now it will terminate and goes out of the RAM. So this P1 is not there into the system at all now. Now P2, which came at 1 into the RAM, was waiting in the RAM for this process to complete its work. Fine. So after this process P1 completed its work, this P2 will come and it require only 1 minute, so it will complete its work at 51. Fine. So this is the Gantt chart in this one. Now let's calculate the average waiting time for this particular case. So the average waiting time in this case will be, that is P1 came into the RAM at 0 and onto the CPU it came at 0. So for P1 waiting time will be 0 only, that is it as soon as it came into the RAM it was directly scheduled on the CPU and there was no wait time for P1. Clear? Now P2 came into the RAM at time 1, but on the CPU it was coming on 50. So the wait time for P2 will be 50 minus 1, that is it will be 49, and there are two processes, that will be 2. So 0 plus 49 upon 2, that will give you 24.5. So 24.5 is your average waiting time, that is the average wait time for process P1 and P2 is 24.5, and that is only because of the process P2. Why? Because P1 was not into the waiting state at all. As soon as it came onto the RAM, it was directly scheduled on the CPU, so there was no wait time for P1. The whole wait time was only for P2. So the average wait time in this case is 24.5. Now come to this case 2. In case 2 again I have taken both the process P1 and P2 with the burst times of 50 and 1. The only difference between these two cases is, in this one I have just reversed this the arrival time, that is in this one it was 0 1, now I am taking it as 1 and 0. Clear? So P1 is coming at 1 and P2 is coming at 0. So let's quickly draw the Gantt chart for this one. So currently we are at time 0. At 0 I will see that P2 has arrived. In the previous case P1 was arriving at 0, now P2 is arriving at 0 and the burst time of P2 is 1 only. So now P2 will start at 0 and it will complete its work at 1. So P2 has completed its work and it will now exit the system and terminate. So P2's work is done, it is not there in the system now. Now we are at time 1. At time 1 we can see that process P1 arrives and P1 will require 50 time units on the CPU. So P1 will start at 1 and it will take whole its 50 units and complete its work at 51. Clear? So P1 has also completed and it will also terminate and go out of the system. Clear? So this is a Gantt chart for this particular case too. Now let's calculate the average waiting time in this case. So the average waiting time in this case is for P1, if you can see that P1 came on the CPU at 1 and in the RAM it came at 1. So 1 minus 1, so it will be 0 for P1, that is the waiting time of P1 is 0, and for P2 came in the RAM at 0 and on the CPU again it also was scheduled at 0 only. So 0 minus 0, so that will give you 0 divided by 2 process, that will give you 0. So the average wait time in case 2 is 0 and the average wait time in case 1 is 24.5. However, we are having same number of process with the same burst time in both the cases. The only difference between the two is that we have changed the arrival times of process P1 and P2 by 1 and 0 in the second case. Clear? So in this one, process P2, who was having a very low burst time, that was waiting for 49 time units for the process P1 to complete its work. But in this one, that same process, since it arrived first, therefore it did not wait it for process P1, it completed its work, and P1, whose arrival time was 1, it also came at 1 in the CPU, and there is no wait time associated with either P1 or P2 in this case. So we have only changed the arrival times and we have got so better results. Clear? So this type of thing actually happens with the FCFS scheduling algorithm, that is called as the convoy effect. Fine. Now one more question. Sometimes it also asks that whether starvation is there in FCFS or not. The most serious version of the convoy effect is the starvation, and the most serious version of the starvation is the deadlock. So first thing is the convoy effect, then we get to the starvation, and then to the deadlock. So we'll study about the deadlock in the in the next upcoming videos. So in this one we don't call this as the starvation. There is no starvation in the FCFS scheduling algorithm. However, the process are waiting for the process having a higher burst time, but then also this is not the starvation. Why? Because in this one we are not following the greedy approach. The CPU is not buying biased. The algorithm is not biased at all. That is, it is saying that if you want to get scheduled first, you need to come first in the RAM. Clear? So if your arrival time is shorter, that is, you are coming early onto the RAM, then only the CPU will schedule you first. Clear? So in this one, we can say that this is not starvation. Clear? So this is the basic concept of the convoy effect, and let's summarize this. So convoy effect is actually an effect in which the process having the shorter burst time wait for the process having a longer burst time. Thank you so much.